Yeah, firstly, thanks, Somen, for giving me this opportunity to learn about TDDFT, not just teach. So, I think in the previous lecture, you got a flavor of time-dependent DFT. It was somewhat of a compact representation of the field for last 30, 40 years, I think. What I will do is I will focus on one small aspect, which is called the linear response time-dependent DFT. And this is, in fact, the main flavor of TDDFT that you use, say, whenever you're trying to run a particular quantum chemistry software. Say, for example, you're trying to figure out molecular polarizabilities, right? So if you're doing that, you're actually behind the hood. What is happening is the linear response formalism of time-dependent DFT, right? And so what are the equations that go behind the hood? So my goal here would be to somehow walk you through, right, in semi-regress form, such that you reach the point where, say, for example, you can go ahead and implement a TDDFT equation if you want. Okay, so that is the point of this. To start things off, I guess I'll start by making sure that we are all in the same, using the same language, right? So let me just ask the following. So if I have a potential, okay, a potential uniquely determines your wave function, right? The exact ground state wave function. Okay, so we'll use psi naught, and from the psi naught we could get a ground state density as well, right? So n0, right? And what does Hohenberg-Cohen theorems tell us? So this mapping is invertible as well, right? So you have this invertible mapping, and all the while this mapping is between ground states, right? So this mapping is exactly one-to-one between ground states. These theorems, of course, don't tell you about existence. So does a potential exist corresponding to a particular arbitrary density? That is never clear. So this is the same problem when you go to time-dependent DFT as well, right? So you have, in time-dependent DFT, you have some time-dependent potential starting from certain ground state, and then you have a corresponding wave function corresponding to that. And then from there, you can also get your density. So everyone okay with that so far? And then what is the Runge-Gauss theorems and the work by Professor Swapan Ghosh and V.M. Deb? What did they tell us? That some of these things are also invertible, right? So you can invert these things. Okay. So again, the existence is not clear. So there is no proof of existence anywhere, again, about these external potentials. And the same thing, once you have this once you have the densities, from the densities you can construct your Kohn-Sham systems, right? So you can construct your Kohn-Sham potentials. Yeah.
When you say time-dependent framework, the external potential gives some time-dependent wave function. Like when you are time-independent case, I know that I can solve xi equal to xi, and h contains your external. Of course, you have to know number of electrons, and then you solve Schrodinger equation, you get the wave function.
Right.
In time-dependent situation, what is the corresponding equation which connects?
So you would use a.
Because in time-dependent Schrodinger equation is a time evolving. It is not like one-to-one mapping between the external potential and the.
Right. So you start from a ground state wave function, and then you evolve it with the potential here, right? So that would be giving you the wave function. But you're talking about the ground state. Mm-hmm. Mm-hmm. Okay. So what should we call this, I guess? So should we call this something else, perhaps? With the evolution that we get?
Yes. So
So, okay. Ah, okay. Okay. Yeah, sounds good. Okay, so
Yeah.
right.
Okay,
So
so to repeat that question, in a time-dependent external potential, you have time-dependent Hamiltonian, and suppose also you know the number of electrons, then you can construct time-dependent Schrodinger equation. That means your external potential is mapped to del psi del t, not psi. That's my question.
okay, so you when you solve for a particular, so what I mean is you're trying to solve for a particular psi starting from a particular v. Is that okay?
Or you can think in terms of a large time interval.
Right.
You do the potential, then you do the potential also. Starting from something.
So if you get that way, that means you are talking about only one time.
No, 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 no.
So then one time
No, you have time evolved and then you got right. So you have time evolved and you got a wave function corresponding to that.
maybe sometimes span.
Right. See, just like when we write, perhaps I think I should not put t. That is a problem. Just like when I write v external of r, I think it's not a single r, right? It is over all r. So it's the same thing. That's what you're. Yeah.
No. R doesn't cause any trouble because it's a total function. R psi is also coming as a R.
Right.
Function of R because I'm solving time.
Independent Schrodinger equation, that gives me straight away H gives me psi, because if I solve H psi equal to E psi, H always gives me psi. That means my external potential along with the number of electrons always will specify proper wave function.
Yeah, but it's
But
over
in a
all.
time dependent
it's-
situation, it is giving me, it is mapping to a time evolution of the wave function, not the wave function.
Okay. All right. Some disagreement there. Right.
What do you think?
All right. So what we do in the Kohn-Sham framework is to construct the corresponding Kohn-Sham potential given a density, right? And this Kohn-Sham system, if I were to ask you the question, is it an interacting system or a non-interacting system? It's a non-interacting system, right? Okay. Right. So what do we do in Kohn-Sham systems in general? We have a very simple.
In a time dependent situation, that inverse map
Between.
Yeah, density alone will not suffice. You have to bring current density also.
Yes, I'm not going into that.
but the way you've written that your inverse map is giving you density to your psi and then to external potential.
You're absolutely right.
Psi equals current.
Yes, so psi requires current density, and also if you want to think about how to construct the Kohn-Sham potential, there is also issues there. So I'm not going into the rigor of that for this talk, right? So just like so we have a Kohn-Sham potential, right? Whenever we have a Kohn-Sham potential, we solve for so-called Kohn-Sham orbitals. Okay, so I just want to establish some language here, and the language that I'm coming to is that of a density matrix, right? So everyone understands density, how to construct density. And again, I'm not using spin variables for this discussion, just spatial variables. So what is the relation between, yes, this is a problem, yeah. So how do I construct density from wave function?
So whenever you tell in terms of n,
Yeah.
you get a solve.
Yeah, so I could use rho, so make sure that, I hope that helps. Yes. So what is rho in terms of, yeah. So rho, so you have wave function, which is many body wave function for the time being, right? And of course, this is a n-dimensional or 3n dimensional integral here, 3n minus 3 dimensional integral, right? If I were to do that, you get density. So that is the map, right? Now we can define something similar, which is called a density matrix. Yes, thank you. Yes. So n is because you have n fermionic electrons here. So because of that, you have to introduce the factor n, right? So what about density matrix? Okay. So that's your density matrix. Okay. So what is the relationship between the density matrix and density? So if I have P of R comma R, that is going to give me density. Is this okay? Yeah. So one important thing to remember is the density matrix by itself need not be idempotent, right? So what do I mean by idempotent? So if I have so whenever this condition is not satisfied, we have what is called as an non-idempotent density matrix. So this happens whenever you have a correlated system, right? Okay. On the other hand, when you have a cone-sham system, so this is so far all about the interacting many-body wave function, psi naught, right? Corresponding to psi naught, you have a non-interacting wave function, which is called the cone-sham wave function, right? How do you construct the cone-sham wave function? It's a Slater determinant of n cone-sham orbitals. Okay. Now, just like before, I can construct the density of cone-sham system. I can also construct the density matrix of cone-sham system, right? So let us try to do that. Okay. So how do we define the density of the cone-sham system? And you know, by the maps, cone-sham theorems and Hohenberg-Kohn theorems, these density, the cone-sham density and the interacting system density, those are going to be exactly same. Okay. So how do you define the cone-sham density given a Slater determinant? Okay. So can we do the same thing like here? So it's the same definition, right? So instead of psi naught, what will I have? I'll have a phi naught, right? The cone-sham. And then now I have a simple Slater determinant, right? Slater determinant is made up of anti-symmetrized Hartree products of all of these. So if I were to do that, if I do this same process, I get a very simple form for the cone-sham density. Okay, so cone-sham density turns out to be just simply sum over P, NP, where NP denotes the occupied orbitals. Is this okay? Right. So this is the cone-sham density, and this is the many-body density. And by this one-to-one map, these densities are going to be equal. Okay. But the other factor, which other question you can now ask, is about the density matrix. Okay. So the density matrix that I have defined here, P. Sorry. right? And NP denotes the occupied orbitals. So the lowest set of off-bow occupied orbitals in cone-sham system, right? So similarly, I can also define a cone-sham density matrix. Okay. So can you follow this logic and define what is the cone-sham density matrix? R comma R prime, yeah. Okay. And in a cone-sham system, right? And let us assume a non-degenerate cone-sham system. You will always have occupancies which are 1 or 0, right? So once you have 1 or 0 occupancies, you would always have a density matrix which will be idempotent. Okay. So P0 cone-sham at the moment, these are spin orbitals. You can consider them as that. Oh, you mean if it's a closed shell or? Yeah, slightly beg to differ there, but yeah. Okay, right. So what you notice here is the cone-sham density matrix is actually not going to be exactly same as the interacting density matrix. The cone-sham density matrix will be idempotent, whereas the interacting density matrix, that will not be idempotent. Okay, that is by definition, because you have a system that cannot be represented by a single slated determinant. The interacting system cannot be determined by a single state determinant, right? As a result, you will have a density matrix that will not be idempotent. Okay, but in the case of cone-sham systems, right, you will have density matrices that are going to be idempotent. Okay, so this idempotency is very important because as we time evolve, right, the cone-sham equations, those are going to be idempotent density matrices. Okay, that is the main point that I want to drive here. Is it okay? So just to summarize here, I just wanted to set the language for you. That is A. The next thing that I wanted to tell you here is that, see, you have maps, right? So when you have all these maps, there is the density is same between the interacting system and the non-interacting system, right? The moment you step a little bit further, you go to density matrix, right? Once you go to density matrices, the density matrices are not same between the interacting and the non-interacting systems. Okay? So this is the main point I want to drive here. Is that any questions here? Yeah. Yeah.
What is the physical significance of this idempotency? Is there any important things that we need to learn about this matrix being idempotent? How it will be affected?
So at the moment, the only significance that I would be using, so whenever you have idempotency, then these can be used as projectors. That is one thing. The other thing is with idempotency, you can be assured that you have a non-interacting state. State, yes, you have single state determinant. So that is when you have idempotency, right? So is this okay so far? Yeah.
Could you please show in a little detail how this is going to be idempotent?
So how this will be idempotent, right? Okay. Yeah. So the first thing you have to also take here is that these orbitals are, these are called 1 electron orbitals, and these 1 electron orbitals are going to be orthogonal to each other. Okay. Yeah. So if I were to take, yeah, and also NP is 1 or 0. Okay, that's the other thing. So if I have, yes. Okay. So I'll just substitute here directly. So I have yeah. Okay, and I have to integrate over R double prime, right? So this will automatically reduce the summation to just one summation over P, right? And once I have that, I'm going to get summation over P and P square sorry, R. Is this okay? And I told you this is going to be 1 or 0, right? So this will give you the idempotence. Yeah. This was also on the fly, so yeah, thanks. Yeah. Okay. This is fine? Yeah. So, right. So between the cone-sham system and the interacting system, right? So I just want to emphasize again, your wave functions are not same. Everyone agrees? The cone-sham and the interacting system. Cone-sham system is a non-interacting system. Interacting is an exact system. Your wave functions are not same. Everyone agrees? Right? The next thing that is not different is going to be your density matrices. Okay? So your one particle density matrices are not the same. What about density? Density will be same. Okay, that is by construction. You construct the potential that so that you get the right density. Is this okay so far? Okay. What about pair density? Okay, you can do this as a homework. So pair density is when I integrate these two functions over all r's except r1 and r2. Okay, that would be pair density. So you can also think about it, right? It turns out the pair density is also not the same. So the only thing that is same is again the density between the two systems. So just keep that in mind. Okay. Yeah. So with that brief detour, right, where I have talked about density matrices and it's one particle density matrix and orbitals and cone-sham states. So I will just now like to move on a little bit, and I would like to discuss molecular properties, right? So I would like to use this language going forward slowly. So let us first start off with molecular properties here, right? So we all know that density functional theory is quite popular, right? So we know that it is used very extensively in chemistry and in material sciences and any other fields where you need some sort of property of a substance, right? And as you know, over time, this has really increased quite rapidly. And what you also notice is that DFT is not only used, not only being used in materials, the use is actually increasing a lot more with time, right? And what do you use DFT for? Not just computing energies, right? That would be actually quite boring. You can also compute molecular properties, right? So that is a point. So this popularity is due to both aspects. Now, how do we compute properties? That is what I will come to here, right? And the other thing that has been really great about density functional theory is that its computational cost is much lesser compared to, say, wave function methods like MP2. Yet it gives you energies which are much more accurate than these wave function methods. Over here, for example, I have shown the atomization energies computed using MP2. This was done a while back by Becky. And also the atomization energies using some sort of LDA type functionals and GGA type functionals. Okay. So what you would notice here is that the accuracy is dramatically improved going from LDAs to GGAs. And this has been one of the reasons DFT has been adopted very, very rapidly. Right. And in fact, if you were to go along the rungs of functions, I know Professor Prasenjit Samal, he is going to be talking about this much more. As you go along the rungs of functionals, this was done over a very large data set by Grimmer. What you notice is that going from LDA to GGA, of course, in terms of energetics, no other properties, energetics, you see a dramatic increase with GGAs. And then after that, the trade-off is not so much. You get a little bit more improvement once you go to meta GGAs or hybrids and other functionals. Okay? Now, DFT is, yes, one, you try to go and use it for energies and other types of static properties, but you can also use it for many of the dynamic properties. Okay? So that is the other reason DFT has become very popular. And in the present age where you want to study how you can harness light, right, to do, say, to generate energy, or if you want to do a chemical reaction, it becomes very important to understand how light interacts with matter. So that is one more reason TDDFT or DFT methods have become very, very popular. And over here, you generally consider hybrid functionals for the usage, right? And these tend to give you very low errors for low-lying excitations. Okay, so here I'm not talking about some somewhat challenging excitations like charge transfer or Rydberg excitations, but I'm talking about, say, excitations in very simple organic molecules, local excitations like pi to pi star type excitations. Okay, so it's very, very popularly used in this context, right? So now let us just step back a little bit. So this talk is all about properties from DFT and then TDDFT. So what are the observables you can get from ground state DFT? And already a lot of discussion has happened, right? You have talked about Fouquet functions, I think, right? So that has been done. So what are the observables you get from ground state DFT? You get energy, right? So you get density, right? So from ground state DFT, right? So you get energy. What else can you get from ground state DFT? Molecular properties. So you have studied some properties, right? So what were those in the previous sessions? Polarizabilities, dipole moment. So these are all the properties that you have learned. You know how to compute them as well, I assume, right? So I'll come to that. Any other properties that you know of? Okay, yeah. All right. So, and perhaps you might have also been, exposed to a lot more properties, right? So you have thought about, say, things like melting points, boiling points. These are much more macroscopic, not really simple molecular properties, right? You have thought about things like magnetic susceptibility, right? Vibration frequencies. All of these are properties that you can get from molecular systems, right? Now you can also get these by using density functional theory, right? So that is a point. So over here, what I will do is I'll try to concentrate on electronic contribution to the properties. There is also the nuclear contribution, okay? And I apologize if I'm repeating anything, just please let me know. I'll run through that really fast, okay? Yeah. Right. Yeah.
Because one wants to, make one thing efficient. As long as you can calculate ground state energies for two different states, and you can relate them to some property, you can calculate all those properties.
You can calculate all those properties. That is correct.
That's precisely what you have. And for polarizability, you will apply a field and calculate another ground state.
Right.
And things.
So that is where I'm going to.
Right,
yes, but this will be very quick. It will not.
This is, kind of mnemonic for remembering what all DFT can give. So
yes.
People, usually when you are in a conference, something people comment. So you got the ground state energy. You got the ground state. So what? Big deal. You got two quantities.
Right.
But without realizing that two ground state energy differences can give you a lot of things like frequency, stiffness, things like those.
Right, absolutely. So that is where I'm going to.
Yeah.
So
I just want to say it in one statement so that students remember. So
yes.
Mnemonic rather than any.
Yeah. No, that is precisely correct, I think. So you can get everything from ground. A lot of properties from ground state energies. That is correct. Right. So I'm going to divide the properties into static properties and dynamic properties. And static is a little bit easier. In terms of energy, you can think of energy differences. So we'll start with that. And then we'll go into the dynamic part, right? So we all know how to represent dipole moment, right? So if we're given a wave function, right, I can write the dipole moment as simply, so dipole moment vector as simply the expectation value of the wave function and the dipole moment operator, right? And dipole moment is a vector. So just remember that, right? So this is quite easy to compute as long as you have the ground state wave function, right? So that's quite easy. Now you can also obtain this dipole moment via perturbation theory, right? So how do you obtain dipole moment as a perturbation theory? And in fact, it has a lot of experimental relevance as well, okay? So I could perturb the system with an electric field, an external electric field, and that electric field is going to couple with my dipole operator, right? So that is the usual way. And once that happens, right, you can write the Hamiltonian as being dependent on the electric field, right? Okay, and corresponding to that field, you can solve for a wave function, psi naught of f. Is this okay? So now everything is becoming field dependent. So in this scenario, my energy is also going to be, energy expectation value is also going to be field dependent. So this very simple formula that I got, right? Now if I were to take a derivative of this, right, the energy with respect to the field, you will see that by using Hellman-Feynman theorem, right, where this wave function is a ground state wave function, variationally obtained, you can get the dipole moment back. Okay, so you're getting the dipole moment just by taking the derivative of the energy with respect to the field. Okay, so you can see when I do this, right, as long as I get ground state energy and I know that this energy is field dependent, I can just take the derivative and I can directly get my dipole moment. That is what Professor Harbola is saying, right? So I just need to take the derivative of the energy with respect to field, and then I get the dipole moment, which is field dependent. Okay. Now, if I want the intrinsic dipole moment, what I would do is I'll take the derivative at field equal to 0, at vanishing field. That will give me an intrinsic dipole moment. Everyone understands intrinsic dipole moment and say something which is a field dependent quantity, right? If you were to evaluate dipole moment at a certain finite field. Yes, so induced would be intrinsic plus the induced part. I think that's what you're talking about. Yeah. Is this okay? Right. So now you can ask, how do I compute this? Right? So now that I have this derivative relationship, how do I compute this? So the way to compute it would be two ways, right? One would be simply analytical formula. Like suppose you know how to evaluate this particular integral. I'll go ahead and evaluate this. That is what I started off with in some sense, right? But suppose I don't have an analytical formula. Okay. How do I get dipole moment in that case? Looking at this. So usually whenever you are asked to solve an equation, they'll say either analytical or numerical, right? So what is the numerical way of solving this? So numerical way of determining dipole moment. Suppose I didn't have formula, right? I only know energies. So I would compute the energy at say 0 field and energy at some finite field, and I'll take the difference, divide by the amount of field, right? So just a finite difference formula for this particular equation, right? So I can use that to figure out my dipole moment. So this is a perturbative approach to figuring out molecular properties. Is it okay? I think that is what you're trying to say, I guess, yeah. Right? So you can evaluate numerically or analytically.
They should have said that rather than you said.
Yes. So, fine. So whatever property you think about, static properties, I can apply a perturbation and I can evaluate this. Right? Right. So that is what you got, the first order perturbation. Perturbation theory, right? So you don't have to stop at first order perturbation, right? I could say, for example, expand an energy, Taylor expand an energy expression with respect to field to any order. Okay. So when I Taylor expand this, right, the first order, of course, the 0th order is your energy at 0 field, and then you have dE0 by dF at say some finite, at 0 field times the amount of field that you have applied, and so on and so forth. Right? So each of these perturbed quantities at different orders actually correspond to different molecular properties. Right? So the first order perturbation is going to give you dipole moment. So this is your dipole moment here. The second order perturbation is going to give you dipole-dipole polarizability. Okay. Is this okay? So if you are interested in computing polarizability, molecular polarizability, okay, and here it is the dipole-dipole polarizability, for example. In that case, how will you do it numerically? So imagine your code, right? Whatever software you have, it prints energies. That's all. Some boring code, okay? It doesn't print you dipole moment, doesn't print you polarizabilities. But you know that energy is coming from a variation there. Yeah. So tell me, so any thoughts? How would you do, how would you figure out polarizability then? You'll differentiate with the field, which quantity? You will double differentiate energy, that is one way. That is, you're going to take more grid points at different fields, you'll compute energy and take the derivatives, you'll get the polarizability, right? Other way would be, say you compute the dipole moment. Suppose your code prints dipole moment. You take the dipole moment at zero field, dipole moment at finite field, take the difference, first order difference, you get the polarizability, right? So this is how you can compute any property in principle as long as your code allows you to add a field, right? So then becomes very, very easy. Okay? So this is how you can do things numerically.
You can write your alpha as del mu del k.
Yes. Right.
Instead of the second derivative, you write it as del mu del.
Okay.
Then give the final.
Right. So these are two ways. So you can get your molecular properties over here. And you could go to third order. At the third order, it is called dipole-dipole-dipole first hyperpolarizability, right? And you could have higher order hyperpolarizabilities. These are all very important from nonlinear spectroscopy perspective. So these are very important to compute actually. Okay. So now similarly, you can also define magnetic properties in the same way, right? So instead of electric field, if you were to apply a magnetic field, right, that is going to couple with your magnetic dipole operator of your system, right? And then you can do a similar Taylor expansion, right? So if you were to do a similar Taylor expansion, right, you're going to get, I think I'm missing something. Yeah. So you're going to get magnetic dipole moment. There should be minus here. And then you're going to get magnetic polarizability and so on and so forth. Okay. So if your code doesn't print magnetic polarizabilities, you can do this very simple thing, right? So these are all different perturbations. Corresponding to a perturbation, you have a property. Okay, that is the main thing here, right? You could also perturb with respect to your nuclear coordinates, right? So suppose I have an energy which is a function of position of the atoms or nuclei, and that is always the case. You can compute the first derivative with respect to nuclear perturbations, second derivative with respect to nuclear perturbations, and so on. Okay. So what happens when your system's first derivative with respect to nuclear perturbation is vanishing? You are at a stationary point. It could be a minima, maxima, right, or a saddle point. But you are at a stationary point. You can now go check the second derivatives and figure out whether you are at a minima or a maxima, right, or a transition state. So each of these has certain value, right? So to figure out, okay. Okay, so you can also have mixed derivatives and so on. I will not go into that, right? And then I'll quickly go to something called local properties, right? Local or non-local properties. These are real space properties, okay? So far I had done derivatives where I'm applying a perturbation which are not, say, spatial dependent, right? So this is some uniform field, for example, I had attempted. So this is not going to be spatially varying, right? But using these derivatives, I can define other quantities as well. So for example, the first one that you see here is the energy functional, okay? So subject to the constraint of normalization. So if I were to take the derivative of the energy functional with respect to external potential, so imagine I slightly change my external potential, which could be nuclear positions or something. If I slightly do that, change that, I get the density at that point. So there is a relationship between these local quantities as well. Okay. I can do a further perturbation of the density with respect to an external potential. That gives me what is called as a response function, chi r comma r prime. Okay. And this is a response function is a term that you'll keep hearing in TDDFT, for example. Okay. And this is called the interacting response function, chi r comma r prime, where you are taking the derivative of the exact energy functional, dE by dV external. Similarly, you also have a Kohn-Sham response function. Okay. The Kohn-Sham response function is a derivative of the density with respect to the Kohn-Sham potential. Okay. So you would start from the Kohn-Sham equation, take the density, perturb the Kohn-Sham potential a little bit, figure out the corresponding Kohn-Sham state. That will give you Kohn-Sham response function. Okay. So density is just R dependent, rho of R, and the second order property, second order response with or first order response with respect to density is R and R prime dependent. Okay, and you can go on and so forth. Okay. So these are all various quantity that you might be interested in. Is this okay? Right. So far I just discussed what are called as static properties. So there is no time dependence in your perturbation, right? Okay. But suppose you're working in a laser lab where you perturb the system with a laser field, right? That laser field will have certain frequency of oscillation, right? So this is going to be a time dependent perturbation that you will have in your system. So once you have time dependent perturbations, the corresponding properties, same way you can Taylor expand and figure out, the corresponding properties are going to be called as dynamic properties. Okay. So static properties, there is no time dependence, and in dynamic properties you have time dependence, right? So over here, instead of perturbing simply with say time independent constant field, you will be applying a time dependent say oscillating field, for example. Okay. So you perturb the system by a time dependent external potential, okay, and then you're going to get dynamic properties. And what are the methods that you use for computing dynamic properties, right? So there are so-called equation of motion coupled cluster methods, which Professor Pal was an expert on, and he discussed some coupled cluster methods with you. You can use even configuration interaction methods. You can also use methods called CC2 and so on and so forth, right? So CAS-SCF methods. And the method that we are going to be interested is linear response time dependent DFT, okay? And that is also, that is perhaps the most important workhorse right now for understanding molecular properties in the presence of a time dependent field, right? Okay. So if you want to understand dynamic polarizability, right? So the one I discussed before was alpha without time dependence. But suppose I want to discuss alpha, which is time or equivalently frequency dependent. In that case, I will have to use time-dependent external potentials, right? Okay, so I think I will now go into the details of linear response TDDFT, right? So where we are going to use perturbation theory, we're going to use certain equations of motion and figure out what are the fundamental equations that are going to form the part of linear response TDDFT. Is it okay? So what we are going to essentially figure out is the same quantity chi, right? But in the time domain. Okay, that is what we'll try to do. And what are the fundamental equations that will work out here? Okay, yeah. So yes, so I think I can stop sharing at this point, and I'll just go to the board. Okay. Yeah. So any questions so far? Yeah. Okay. So any questions on the density matrix side? No? Okay. So maybe I'll just repeat one or two things. So I'll just write down the Kohn-Sham density matrix again. Hmm. To start off, it's in the ground state, and I'm going to apply a small field.
So you're not doing anything, the molecule is already excited and then you would
No, that would be a 2-photon or a higher order perturbation, I think.
because in that case the functionals will be complicated. Don't know excited functionals.
Right. In the linear response domain, you can still do 2-photon properties. Right. We can use, yes. How accurate they are, that is. Okay. So what I'll be discussing now is called as and I hope you can read it. Okay. See what Professor Swapan Ghosh discussed, right? He had actually introduced also linear response TDDFT there, but he also mentioned that see if you were to actually propagate your Kohn-Sham equations in a time-dependent fashion, right? At each time you will have to solve them self-consistently. It's a little bit of a hard problem. But in practice, what we do in most of the codes that you have, you use what is called as linear response TDDFT to figure out the molecular properties. Okay, and it does a quite decent job and gives you excitation energies. It gives you other types of molecular properties. Okay, as long as you can work in this linear response regime. Okay, so we are going to discuss this. Some of the references I just want to give here, which are very important in this context. So one is Casida. This is ChemPhys letters. I don't have the year here, but yeah. Just share the papers. Yeah, yeah. Okay, yeah, I'll do that. Yeah. So these are a couple of papers that you should be interested in. Yeah, so I'll just share those with you. Okay, yeah. So I'll just introduce a couple of things here. Again, I thought I'll finish in half an hour. Yeah.
So, for students in particular, there is a fantastic use of modern physics by Carpus, Langhoff, and Einstein.
Okay.
I think it was in 1976 or so. I think students should read it. It's absolutely superb if you want time-dependent quantum mechanics.
Okay.
Perturbation theory, how it is to be done.
Yeah.
It really brings out nuances.
Okay.
So you may just
Can you read the authors?
author is Carpus, Langhoff, and Epstein. Epstein is the old one, SCH.
All right. So yeah. So this is a real space representation of your Kohn-Sham density matrix, right? So we can also have a matrix representation. So I just want to quickly define that. Yellow. Okay. Yeah, sure. Sorry, I have. Okay. So this is your Kohn-Sham density matrix. I'm going to just denote it by 0, which means 0th order, right? And if I were to write this matrix, I'll just erase this part. So this is going to be a dimension of, say, m by m, where m is the number of Kohn-Sham orbitals, both occupied and virtual. And this will consist of, say, certain ones in the diagonal followed by zeros. Okay, so the block of ones will be, say, a dimension n by n, where n is the number of electrons in the system. Okay, so now can you tell me, in this matrix form, right, the density matrix, is it now idempotent? So say P0 times another P0, will I get P0? I'm going to get P0, right? So this is an idempotent density matrix in this form, right? So how do you get the Kohn-Sham orbitals? You're going to solve a Kohn-Sham equation. Okay, so these are the Kohn-Sham orbitals which you get by solving this one particle equation. Okay, so this particular operator, sorry, this is T, kinetic energy. Yes, so T plus V Kohn-Sham, we generally denote it by, say, sum F0, the 0th order Kohn-Sham operator. I'll just remove Kohn-Sham for the discussion. Okay, so that will be my Kohn-Sham operator in the 0th order. Is this okay? Now I could also have a matrix representation. Okay, which is going to be, say, okay, and if I were to write this again in the epsilon language, this is going to be, say, epsilon p delta p, right? So if I were to now write the Kohn-Sham matrix, that is going to be consisting of, so can you tell what would be the structure of the Kohn-Sham matrix based on this? So the diagonal will have epsilons, right? And how many epsilons? M. Okay, both virtual and occupied, right? So you will have epsilon 1 all the way up to epsilon. Okay. So if I have my Fock matrix, right, and it is in so-called canonical form, right, I'm going to only have diagonal values of epsilon here. Okay, that is a point here. Is this okay? So this is a matrix representation of this particular system. Okay, so now our job is to figure out the linear response to density of the system or density matrix of the system in the presence of a perturbing potential. Okay, so P0 is my Kohn-Sham state, right, in the absence of any perturbation. So a ground state of a molecule, right? So now I want to understand how the system will evolve in the presence of a time-dependent perturbation. So that is the problem over here, right? So what would be the equation of motion for that? So I have, right. So my question here is the equation of motion, okay, for a cone sham system. Okay. Yeah.
Whenever we are speaking about response, we are essentially speaking how my densities change with the change in the external motion.
Right. Over here, it will be a density matrix, but the density response is contained in the density matrix response. Just because I showed you the density can be obtained from the density matrix. Okay. Yeah. So what would be the equation of motion for that? I think Professor Sapan Ghosh very briefly discussed that, right? So what we will be doing here, you can do a couple of things. You can start from the action formalism and go forward. I'm going to keep things very simple. So what I will do is I will just evaluate I will evolve the cone sham system just based on time-dependent cone sham equations. Everyone knows what are time-dependent equations of motion for an exact wave function, right? H psi equal to I d by dt psi, right? That is the exact wave function. Now for the cone sham system, you can think of something similar. You have F cone sham operator acting on your orbital p, giving me I d by d. Okay, is this fine? Now what I will assume, so you have one equation for say for the kets, you also have an equation for the brass, right? So you have the same equation. So what I will do is I'll try to slightly generalize this. Instead of using this equation where I have the canonical form, I'm going to use a non-canonical form, right? So in that particular case, I'm going to have, say, F QP okay. I hope I'm not making a mistake here. F over Q, yes. Okay, and I would have an equal equation for the complex conjugate of that, right? Okay, so I can add those two up, right? And I'm going to get a very simple equation of motion for the cone sham matrix. Okay, so this is my central equation of motion for a time-dependent cone sham system. Okay. It's also called as a von Neumann type equation of motion. Okay, so this is, you could just get it from using this equation and its complex conjugate. You can get this particular form. Is this okay? Right? Okay. Fine. Okay. Any questions so far? Right. So what you could do is you could just expand P, right, in this representation, say in this particular representation of P, and you would get this particular equation. Yeah.
So you're writing this FPS operator,
Yeah.
two seconds on the time.
It at the moment, yes. Yeah. Yeah.
On top. On top. FPS top.
Oh yeah. Yeah. Okay.
So it's including everything.
It's including everything. Right now, it is including.
Perturbation is the full.
It's a full thing. Yes. Okay. Yeah. So I'm going to be adding a perturbation to this, and then we are going to see how the system will evolve. Okay.
The perturbation from that TXT itself, right? Because the written FPS is function. That's what I wanted to clarify.
Okay.
FKS.
Yeah.
Now you want to expand 5P. I mean, the perturbation you've already added when you wrote that function, right?
Right. So this FKS will contain an F naught, which is time
Not plus the
plus something. Okay. Yes. Yeah, that is correct. Okay. So what I mean by this in expanded equation form, right? Okay, this is a commutator here, FP commutator. Okay, so now, while this system is evolving, we have one constraint, right? The constraint is on the P. We should always have a cone-sham type state. So what does it mean in terms of density matrix whenever we have a cone-sham type state? So did you understand my question? So if I have do you guys remember when I discussed, say, we had interacting system wave function and a non-interacting system wave function. How do the density matrices behave? One is an idempotent, other is non-idempotent. Okay. So now when I'm time evolving and I'm saying my system is going to be always a cone-sham type state, okay, or non-interacting type state. So what would be the constraint on the density matrix? It has to be idempotent. Okay. So while I'm evolving, always you have to remember that my P of t times P of t has to be equal to P of t. Okay. Fine. So this is the exact equation of time evolution. Now what we will do now is to just focus on the linear response. Okay. So what do I mean by that? So any questions so far until here? Okay. So far I have not considered a linear response. Okay. So I applied a perturbation. That perturbation has gone into this cone-sham matrix. Okay. And I'm trying to evolve my system. What I will have to do is at each time point, right, I will have to solve my fees, and those, remember that f is going to be dependent on fees, right? So this has to be in a some sense self-consistent way, right? So that has to be done. What I'm going to do now is to consider only the linear response of this. Okay. Yeah, so it is
self-consistent solution for a time-dependent problem.
So what I mean is for f, right? F is a dependent function on fees. Those fees and the eigenfunctions, those have to be the same. Not eigenfunctions.
In general, when you talk about self-consistency, what do you mean? That you start from some trial step and just you reiterate until you achieve some whatever
So,
energy
okay.
minimum or whatever requirement you
So
have.
you have to
But
solve.
when it is it itself is evolving in time, and then you can stretch that and do some iteration on self-consistency to reach what?
So you
They
need
must
to,
have some goal.
right. So this has to be a non-linear equation, right? So this, you have to have the same fees on both sides, right? So this is a non-linear differential equation that you have to solve for. Is this okay?
But your if you choose a self-consistent, then your AP would be 0, right? That commutator.
That is right. So
That's what will happen if you like do it for the ground state Fock matrix and the density matrix. Then it will come out to be 0. But that doesn't happen. That's not. If that
so
happens,
it's not the
then
exact. It's not the exact sense of self-consistency. What I mean here is that your f is going to be a function of fees, right, and more perhaps, right? So and that is which one? So my goal here is no. See, this is the I think this is the thing that Professor Professor Sopan Ghosh had discussed about how to solve this equation, right? So which is in a non-linear, I mean beyond linear sense, in a non-linear sense. Okay, so if I were to solve this equation in a non-linear sense, okay, that is why I kept using the word self-consistent, like not really self-consistent. So if we were to solve this non-linear sense, something like that.
On that time slice, you are doing something so that there is no more change in that set of orbitals. Again, you go back after time evolution to the next time slice, then do again the self-consistency.
That also we are not doing it.
So in the
in each time step, we don't really optimize the orbitals.
So if you're talking about the real-time TDDFT, that is not this.
But we use the same equation there also.
But I think it's still linear response in the real-time TDDFT.
Real time also is linear response.
It's linear response. So I'm saying this is not linear response.
What is self-consistency?
So I don't think I know the answer for that. I'll give it to that. So what I do mean here is that this is a non-linear equation that you have to solve for, right? Okay. So we can discuss this. So what I mean is here you do have a non-linear equation, right? That is the main thing. Now whether are you minimizing it? You're not minimizing anything. I think if that is what you're asking.
No.
So it's not a minimization, right? So that is there, right? Right. So
Your point is we are using these consham orbitals again to construct the Fock matrix.
Fock matrix. Yes. So it is a non-linear equation to be solved for, right? Yeah, but yeah, something to think about. So what I am going to be doing here is a linear response, right? So figuring out if I were to perturb this system, right? How does P evolve, or what is the linear response of P? So that is the main goal of this discussion, right? So it's okay. Right. So can I just go back? So let us think of a perturbation, right? See, normally when I think of a perturbation here, right, so it should be, say, some local perturbation, say V of R, with some time evolution, right? But because I'm using a density matrix formalism, so my perturbation So I used a perturbation which is deliberately Hermitian, right? And we'll be interested in figuring out the response of this system in the limit when FPQ is going to be 0. We'll see what it gives us. Okay, so that is the ultimate goal of this discussion, right? So once I add this perturbation, so my Fock matrix okay, so that would be the perturbation of my Fock matrix. So once I do this, okay, so once I add this perturbation to my system, or this is the perturbing potential that I have to my system, I'm going to expand my wave function as some P0 plus say some P1, which is time dependent, and so on and so forth. Okay. So that would be my time dependent evolution of the density matrix. Is this okay? Now, what was the constraint again on the density matrix? It has to be idempotent. Okay. So what that means is when I do this order by order expansion, right, this idempotency has to be retained. Okay. Is it okay? So we have to have okay. So if that were to be satisfied, right, we will have, based on this order by order expansion, right, okay. So this particular equation has to be satisfied if you want to retain idempotency order by order. Okay. Is this fine? Yeah. So small fp, this one. So this is my perturbation. Okay, so it's a non-local perturbation that I have added to my system. Yes. So I have a general time-dependent perturbation to start off with, and I'm just representing one of the Fourier components of this particular perturbation. Is it okay? So my interest is I'm going to have one Fourier component, and I'm going to ask how my response is with respect to that particular Fourier component. Yes, so we have chosen this form so that the density matrix, not just the density matrix, also your Hamiltonian, it's going to be Hermitian, not idempotent, right? Okay. So, right. Is this okay? And what we have to figure out is this particular P1. I'm now going to assume a simple form for P1. So P1 is say going to be equal to, again, a similar Fourier component. Okay. So let us think about this. What is P1, right? So I started with a P0, which is idempotent, and I'm perturbing the system, and I'm figuring out how my wave function has evolved. right? So whatever Kohn-Sham orbitals I had at time t equal to 0, after adding the perturbation, those are going to slightly change. Do you agree? Right? So that change is represented by P1, right? And I have now written a general form for that P1, which is quite consistent with the perturbation that I have put in. Okay. So what are these elements? dpq and dqp. These are the elements that you have changed in your density matrix. Okay. The small changes to your density matrix. Those are these small component dpq and dqps. Is this okay? Now let us just ask a very simple question at this point. So you would like to ask, is dpq, right, that we have here, will all the terms contribute or only some terms contribute here? Okay. So for that we can use this condition P1 P0 and P0 P1 is equal to P1. And is this equation okay for everyone? Yeah. Okay. So let me just start by that. Maybe we could, I don't know how I'm doing with time, I guess. 10 minutes more. So maybe I'll just stop here and I could continue tomorrow whenever. Yeah. So I'll just take 5 or 6 minutes and then I'll complete this part. Yeah. Okay. So based on this condition, so can you tell me, so what is the dimension of the P matrix? M by M, where M includes occupied and unoccupied orbitals, virtual orbitals, right? So this dimension of D matrix, the small d matrix is also the same, okay? But let us see if the D matrix, right, that we have here, do all the components contribute or only few components that are going to contribute? Okay, so that is a question here, right? So can we make use of this equation to figure out which components, right? So let us first expand this, right? Putting these things in there, right? Okay, so let us say we just focus on, say, the e power I minus I omega t terms, right? So in that scenario, we're going to get okay. Okay, so far? Yeah. So what are the simplifications I have here? So if you remember the form of P0QR, when is it non-zero? So P0 is diagonal, right? So there are only ones for the occupied orbitals and then you have zeros, right? So in that scenario, how does this reduce? So let us call the occupied indices by I, right? So you will just reduce to PII, okay? Or let us say, Is this fine? So what about the remaining? I hope I'm not making a mistake. I think I made a mistake somewhere here. Making some mistake here. Okay. So any thoughts so far? Is this okay? So from here to here, any problem? Is this fine? Yeah. So this one is supposed to be idempotent, right? And then you have in the diagonal, you have occupation numbers only, right? So in that scenario, right, so this particular element would reduce to delta QR NQ. You have occupation, otherwise it is, otherwise it's zero, right? Is this okay? And then similarly, you have a term on this side. Yes, so finally, so I'm making sure that there is no mistake here, right? You have to make sure that there are only. Yes, this is the Kohn-Sham basis, right? So we are going to figure out whether you're going to get, yeah. And things are okay on this side, right? The same formula. So summation over NQ, sum over Q, delta QP, right? PP, QR. So let us take the case where, I don't know if I made a mistake anywhere. Just hope I'm not making a mistake here. Yes, so only occupied, unoccupied pairs have to come out. So over here I have NR, so NR is occupied, then why am I thinking so much? Yes. Okay, so I don't know if it makes sense. So what this means is that you should have either NR to be 1 or NP to be 1, right? So what this means is you can only have elements which are contributing to P1 should be occupied, unoccupied indices, right? If you have occupied, occupied or unoccupied combinations, this will not be satisfied. Okay, so this is the final thing. I'll try to do it in a better way, but this is the result. So what this means at the end of the day, so okay, so what this means is for this evolution, right, in the first order, the only contributing elements are, say, D occupied, unoccupied, or D unoccupied, occupied. Okay, so for example, elements like these, DIA or DAI, those are going to be contributing. Is it okay? So where I denotes occupied orbitals, this is the common language we use in a lot of quantum chemistry, or A are unoccupied orbitals. Okay, these are the only elements that are going to contribute. The rest of the terms are going to be vanishing. Is this okay? Yeah. So maybe so we'll stop at this stage where I have just discussed what are the contributing factors of your first order perturbation to the density matrix. Now what is remaining is to figure out the equation for this, right? How do I get this, right? So for that, we have to do a little bit more derivation, but I think we will do it with slides. So with that, you will get the final linear response TDDFT equations. I think this is, we can try that. Okay, so we'll, yeah.
Density matrix that you are representing.
Uh,
So far, there is no linear response entered into the picture, right?
So, okay, so the P1 is a first order response. Okay, so, and the response, so this is a first order response with
First
respect
order with respect to the external
with
potential.
respect to the external perturbation, right? So this is the expansion I have done. P of t is P of 0 plus P1 plus P2 and so on. So you can have a second order equation, same idempotency
Here you are truncating to P1.
to P1. Yeah. Okay. And I'm figuring out the equation for P1. That is the end goal here.
P1 is essentially basically your density response functions, right? What P1 you are having here.
P1 is the response. The response function will be the kernel that will connect your perturbation, the V external, the G, and your P1. That would be the response function.
So I'm trying to think. So these are like, it's kind of intuitively, if you think that then only occupied, unoccupied, those pairs should contribute.
Yes.
So if we go to this higher order term,
Yes.
they should also come, because occupied will never come into play, or unoccupied. So still they will contribute to the same type of terms, right? Even if we go to the second order perturbation and third order, isn't it?
So I'll have. Yes, right. In the first order, it is occupied, unoccupied. You are trying to say it is beyond first order as well.
And I'm trying to think that what will happen if I go to second order. What are the other options I have? Like, it can be multiple occupied, multiple unoccupied.
Right.
That is also, again, ultimately, if you look at the density matrix, it will turn out that those are the off-diagonal element that has some number, others are 0.
So, I mean, yes, intuitively thinking, because that is the only perturbation you'll have. That is the only rotation you can have.
Possible we have.
Yes.
We have.
Right. Yes. So you can go for the second order response if you want. Then you will have a.
In that case, you will have unoccupied, because once it gets occupation, it will again get excited.
Yes, that is not clear. So, but everyone can see. I guess you will have a different equation for that,
Yes.
right? Right. So
This one also, that means only you will be able to capture the single expression.
not necessary. Not necessary. No. So unless you assume the adiabatic approximation, at this stage you are capturing everything. You're excited because see, your system is always cone sham. You're starting with that. Basis is unoccupied, occupied, but the number of poles that you get is not going to be occupied, unoccupied poles. The number of poles will be much more. Yes, that is what is supposed to be obtained. No, not necessarily. So it is folded in. All the higher excited states are also folded in the linear response.
So if you didn't have the adiabatic approximation, then we would have gotten all excitations with it.
Yes.
Yeah.
Yes.
It will still occupy. It will still remain unoccupied, occupied, but more electrons will come. Total number of excited electron will be more than one.
Yes. So I mean, think of this like the what is that partition EOM, right? So you could partition an equation of motions couple cluster theory. You could partition it and fold it back such that you get So you get higher order excitations even in a smaller space of say particle hole basis, right? So 2 particle 2 hole basis can be folded into the particle hole basis. Okay. So that appears as the frequency dependence. No, no. If you look at the pole structure, you will be getting higher order excitations. If it is a correct kernel, you will be getting higher order
We
excitations.
can have the discussion after. Okay. Is there any question from the students?
I still don't understand it. Does it mean that if I consider first order perturbations, then only the orbitals which have only one electron, they will only contribute? I mean, you are saying occupied, unoccupied. What does it actually mean? Does it mean that if I have doubly occupied or doubly totally vacant, they will not participate? Is it like that?
Here we are speaking of spin orbitals.
Okay.
Yeah, no. It's not like that. See, so you're trying to describe your excited states as well as your perturbation here in the basis of cone-sham orbitals, right? So how do you want to describe them in that basis? So that basis consists of pairs of this excited states where you have one unoccupied, one occupied. So this particular matrix elements, I shouldn't call excited states. So these matrix elements, right, will have contributions where one of the index is occupied, the other index is unoccupied. Just because of this particular condition, which I think it's correct, I'll just verify. Okay. Yeah. So I'll verify that and come back. I think that is correct.